So we're now going to try and solve the KDV using this method. It's not sort of totally obvious why this method is going to work so well. And it turns out this method is the best way to solve the KDV. It's certainly the easiest to program. And lots of people tried lots and lots of different methods to work this out. It's far from obvious at the start. So this would have been cutting edge research probably 20, 30 years ago, what we're doing, or maybe 40 years ago. All right. So here's the KDV. Remember it has this funny 3 here, and we worked it out because it's to do with integrating twice. No, sorry, integrating u squared, you get divided by 3. If we didn't have this term here, we get shock swarming, but this punishes the shock because anytime that the wave starts to steepen, this will dominate. The third derivative grows rapidly and dominates and suppresses it. So now we take the Fourier transform of this equation with respect to x, obviously. So we're assuming here that x goes from, there's no boundary conditions. So the solitons, we've got these weird sort of solitary wave solutions that we're going to try and experiment and discover numerically, and we're going to look at how they travel and all this stuff. So d by dt of u hat plus 3 times, and it's the Fourier transform, it's ik times the Fourier transform of u squared. Not the Fourier transform of u squared, something quite different. So actually what we're going to do in this method is we're going to solve it in the solution, we're going to solve it in, we're going to live in Fourier space and we're going to solve here. All right. Right, so we write this as the following. Alright, I've got rid of the minus here by cubing only the k. So what we've got, this is the method here. So we're going to solve, the idea of the split step method here is quite simple to understand. We're going to solve at each time step. So we're going to go from, we're going from t to t plus delta t. We're going to just advance this forward by a tiny time step or a large time step, depending how big, up to us to decide that. We're going to solve the time derivative of u is equal to minus 3ik u squared hat, and we're going to solve, or we're going to solve, not or, we're going to solve one followed by the other, u hat. So we're going to solve we're going to time step for this amount and for this amount, and we're going to alternate it. So this is the scheme. So the first thing we do, we can solve this equation. The second one we can solve exactly. We know how to do that, d by dt, and we're in Fourier space here. So u hat of t plus delta t, if we advance it by a small time step, is just going to be equal to the solution at the time step multiplied by e to the I k cubed delta t. So that's how we solve exactly. That's the exact solution. But it's only the exact solution for this part is equal to this part. And then we're going to solve d by dt of u hat equals minus 3ik u squared Fourier transform. We're going to say that u of t plus delta t is equal to u of t, so it's u hat, I should be careful here with a hat, the old solution, plus delta t times 3ik minus times u hat squared. So we're just going to use Euler's method. Could be clever about it, but we're not. We're just going to simply time for, and we're going to calculate this thing here using the Fourier transform. So what we're going to do, we're going to solve each time step. We take the solution forward once by that exactly, and then we take that new solution and we take it forward here using the Euler's step. So we get a split, that's why it's called split step, because we're splitting the steps and we're exploiting the fact that we can solve one exactly and we're solving the other by Euler's method. You could sort of decide what the heck I'm going to solve this and add an Euler's method on here and not solve this exactly. It doesn't make a huge amount of difference here, but sometimes it's kind of, you know, nice to be a bit clever, isn't it? So let's have a look at how that's going to work in practice. So we form this U1, this intermediate step at t plus delta t is equal to u hat of k comma t, the old step, times e to the I k cubed delta t. And of course we can do this, that's just, we've got to make sure we have the right values of k, but it's just a multiplication. And this is the intermediate step. So this is the intermediate step. We're going to delete that. We don't need to, we're not going to save that. But k comma t plus delta t, this is equal to the old value, which is, we've got to make sure it's not the old one, but the old one with the, at least done that step, otherwise of course it will be forgotten and won't happen, minus 3ik delta t times the Fourier transform of that squared. Okay, and if we want to go into the actual process here of how to do this, what we've got to do here is we're going to go u hat 1, right, plus minus 3ik delta t, and then it's the Fourier transform of the inverse Fourier transform of u1 and then squared. We need another bracket around that. Okay, so we take the function itself, we inverse Fourier transform, so this is u1 hat, right? This is the intermediate step. We inverse Fourier transform it, so we get back to the u space, then we square it, and then we Fourier transform and advance it like that. And the Fourier transform was just done as a command in MATLAB. I didn't say that. Actually, I completely forgot to show you that in the previous slide. Whoops. Let's have a look at that. Yeah, sorry, I was being so clever. I forgot to say that the fast Fourier transform was just a command FFT, and the inverse Fourier transform is just a command IFFT. So you can Fourier transform using FFT of f, that takes you to the Fourier transform space, and you can inverse Fourier transform using IFFT. And these are numerical versions of the Fourier transform. We'll talk a little bit more and a lot more about how they work and the theory of them, but right now we're just going to assume that we're going to accept that we can Fourier transform a function using this command, and we can inverse Fourier transform using this, and that the k that we use is got to be given by the special formula. Okay, I'm going to stop this video here, and then we're going to go on and actually do the code and look at the MATLAB code and solution for the actual KDV equation itself.